Hello, my name is Jin Young Moon.
I'm Charlene Teachout.
Yes, and I'm Fabian Tambiano.
The paper we chose titled Non-Deterministic Finite Automata, Recent Result on the Descriptional and Computational Complexity. These are the topics we are going to cover in our presentation. Instruction, determination, and simulation of NFAs, minimization of NFAs, lower bound techniques, language operation problems. Deterministic finite automata are defined by the following quantable: M equal Q sigma delta Q0 F, where Q is the finite set of states, sigma is the finite set of input symbols, Q0 is the initial state, and F include Q the set of accepting symbol. The transition function is characterized by delta. Q times sigma produce Q. Thus, starting from Q0, if there is a sequence of possible moves ending at a final state, then the NFA accepts the input string, otherwise it is rejected. Along with non-deterministic finite automata, which has similar structure, but a transition function that is defined as delta, Q times sigma produce 2 to the power of Q. The rest of this video will cover determination and simulation of NFAs as well as 4 theorems that relate to DFAs and NFAs. Determination is a technique used to convert an NFA to DFA. Using simulation on DFA, NFA, two-way NFA, and two-way DFA. We can use the subset construction technique. Each state of NFA is set of states of NFA. The initial state of the DFA is the epsilon closure of the initial states of the NFA. Simulation can be done through Z motion using closing sequences. Here is a conversion example of NFA to DFA. 0, 1, 3 states are converted to the initial state of the DFA. Transition A read leads to 1, 3, 2 states combined. Transition B read leads to 1, 3, 2 states combined. Transition A read leads to 0 states. From states 1, 2, 3 transition, B read leads to state 1, 3. A loop in state 1, 3 by reading B is produced. And from state 1, 3, reading A, we move to state 0. There are 3 final states: 1, 0, 1, 3, 1, 2, 3, 1, 3.
Tight bounds result. Tight bounds are basically between, it's used to calculate the complexity of a computation. It's then the time it will take to compute a certain operation. It's between big O notation and omega. So here, this is a table that shows us what is the result found, and you can see that to convert an NFA to an DFA, it can take you 2 to the n complex time to convert that, and you can also see that to do the same conversion from 2 DFA to an NFA, it gives you a certain time. And basically, the result found that states that two-way DFA are very powerful with respect to the number of states they produce, because they produce less states. So there is a theorem. According to that theorem, basically when it comes to determinization, we know that NFAs are considered NP hard. And what is NP hard? It's when you're solving a problem in polynomial, makes it possible to solve all NP problems in polynomial time. And then if we move to minimization of NFA, we know that in class that two NFA machines are said to be equivalent if the language produced by both of them are equivalent. And based on that theorem, we know that the conversion from NFA to DFA is very possible and easy. So also we can say that also that conversion of or minimization of NFA can bring a very well-known problem called p-space, and p-space is described as a problem when the problem can be solved by an algorithm that uses an amount of space polynomial in the size of its input. So based on that, the NFA to NFA minimization problem is p-space complete, which state that it's practically impossible to minimize it because the number of states grows rapidly. So there's a law-bound technique that we use, and that technique is used to measure the size of finite state machine. One theorem very known is called Myhill-Nerod theorem.
So now we're on to language operation problems. Regular operations on languages consist of union, concatenation, and star. The complexity of a language is determined by the number of states that it generates. Here's an example of a union. Here's an example of a concatenation. And under the union operation, for m belongs to m1 and n belongs to m2, m plus n plus 1 states are efficient for the worst case to accept the language generated. Under the concatenation operation, m times n states are sufficient. Here's a table demonstrating the complexity for DFAs and NFAs on finite languages. And in conclusion, determination is a great tool that can be used when memory space is a constraint. It can be applied to NFAs, DFAs, two-way NFAs, and two-way DFAs. And techniques such as fooling set can be used to measure the size of those machines and the complexity related to computation. Computation can be expressed in linear, constant, or impossible depending on the machine used.